Hello class, welcome to our second online lecture. So I'm just going to get started. Today is lecture number 15, still on chapter 8, quantum statistics. We're going to go over stuff that's on pages 354 to 364, and actually we're going to be following the text a little more closely than we usually do, so it might be beneficial to, or rather it will be extra beneficial, because it's always at least a little bit beneficial. It'll be extra beneficial to read the text, and either before, you could pause and go read it, or after this. And for next class, we're going over 493 to 521. So next class we'll be starting nuclear physics, so this will be the last lecture we have on quantum statistics, and sometime over the weekend I'm going to figure out what's the deal with homework and how I'm going to do that. Okay, and then I'll assign you some problems from the quantum statistics chapter. So last class we got those two distributions for quantum statistics depending on whether we have bosons, integer spin particles, or fermions, half integer spin particles. And fundamentally, the reason for that is that we count bosons and fermions differently, and they behave differently when they're brought into close proximity. So of course, things happening at small scales is the thing we're interested in quantum mechanics, so that's going to be a salient thing to talk about. So to remind you, we have the Bose-Einstein distribution. Right? So this is for bosons, integer spin. And that is given by FBE as a function of the energy, E the alpha, the normalization, E to the E kt minus 1 under 1. And then we have our Fermi Dirac. And this is for fermions, half integer spin particles, and the Fermi-Dirac distribution as a function of energy is very similar to the Bose-Einstein. Right? E the alpha times E to the E under kt, this time plus 1. So again, a trick to remember is that the plus 1 in the denominator is the opposite of the anti-symmetric wave function, where we get a minus 1 if we switch particles and look at how the wave function changes. And then, of course, for the bosons, we have the symmetric state, we have a plus 1. So that distribution we have is the opposite, so that's just a little trick to remember. So quantum mechanically, the differences between these two things, as I mentioned, is how we count different things, how we count particles, which counting and statistics are very closely related. So let's look at the probability. We find two distinguishable particles in the same state. So essentially what we're talking about now is the Boltzmann distribution, the classical distribution. So the wave function for these two classical particles, i.e. distinguishable, but still we can write wave functions for them. Right? If we switch the two particles, right, suppose we have one over here, and we switch them, this wave function changes. And now we'll take the case of them both being in the same quantum state, possibly the ground state, possibly some other state. And because those two things reversed are the same, we also have, oh no, that's not it. We also have in their wave functions, right, that they're the same. We just multiply them in a different order. So this is just the Boltzmann distribution, so that B is for Boltzmann. So then my wave function, or rather my probability, is going to be psi star psi for the Boltzmann distribution. And I wrote this down just to show you that it's not weird. Like, there's nothing weird happens. The probability of finding some particle in a Boltzmann distribution to be in some specific set of states, I just take the wave functions of each of those individual particles, right, and multiply them. So if we rearrange this, just to maybe illustrate that, I mean, I'm writing the exact same thing. I'm just changing the order of the multiplications. These two particles separate out. We have essentially one wave function for one particle and one wave function for the other particle. We multiply them together. It's the same as we have over here. So nothing quote unquote weird happens. Okay. Okay, what about Bose-Einstein? So here we have 1 over root 2, our normalization, psi n, particle 1, psi n, particle 2, plus psi n 2, psi n 1. Okay. So here, these are two quantum indistinguishable particles. And because they're indistinguishable, we don't know whether one's on the left or one's on the right, or one's on the right, the other's on the left, because there's fundamentally no difference between those two things if they're in the same state, right? If I take two photons, which have the same frequency, right? We can think the frequency, the energy, being their quantum number. If I take two bosons of the same frequency, of the same quantum number, and I switch them, right? If I play like a shell game where I put the two photons under some cups and I move them around, right, and I lift them back up, there's no way for you to tell which boson was originally which because they're indistinguishable. So I add those two possibilities in superposition because I don't know which one is which. And not only do I not know, the universe doesn't know. So therefore, I have to write these two wave functions in superposition. Possibility that the boson, or the first boson is in state n and the second boson in state 2, and the other way around. Okay, and we have this plus sign here because this is an erase the last 3 seconds. We have this plus sign here because this is a symmetric state. In other words, when I switch these two particles, that's the same wave function, right? And then I have the same wave function there. So because I can just algebraically rearrange this, I can rewrite it as 2 over root 2 psi n 1 psi n 2. So I can just add these together, these two possibilities, and I get 2 over root 2. Now if we want to look at the probability that both of these bosons are in the same state, in the same place, we have to take this guy starred with itself. So we end up with 2 n star 1 psi n star 2 psi n 1 psi n 2 equals 2 psi be star psi be. Oops, no, sorry. Just B. right? It's twice this guy here, because we have this 2 out front. Right? Maybe this is a bit more clear. So thanks to this quantum indistinguishability, which means we write this initial state in a superposition of these two things. Right? When we don't have knowledge in quantum mechanics, that means that both things are happening. Because of that, we get the probability that both of these things are in the same place at the same time as twice what it would be for the Boltzmann distribution. So what does this mean? It means bosons like to hang out in the same place at the same time, because the probability of doing so is twice what it would be if they were distinguishable particles. So this is an effect known as bunching, that bosons kind of like to sort of vibe, you know, hang out in the same place and just sort of chill. Bosons are chill. Which particles are not chill? The Fermi-Dirac particles. And then if I write this same superposition, well, when I know when I switch those labels here, I switch my 1 and my 2, I pick up this negative sign because Fermi-Dirac's statistics is with this negative sign, an anti-symmetric under flipping to Fermi-Dirac particles, which, as we saw last class, is 0. All right, so fermions can be said to anti-bunch, so bosons bunch, fermions anti-bunch, which means they don't chill out and vibe in the same place. Like, they don't like each other. They don't want to be around each other. Okay. So we see that for each of these 3 cases, right, Boltzmann, Bose-Einstein, Fermi-Dirac, we get different ways of counting things. Okay, because things either are in the same states as much as they normally are with classical particles, or they're more likely to be in the same state, or they're impossible, or it's impossible for them to be in the same state. Okay, so the next obvious question is, well, what if we have some system, right, and we know like pressure, temperature, all the other kind of stuff, but we don't know whether or not we should use the Boltzmann distribution or the Bose-Einstein or the Boltzmann distribution or the Fermi-Dirac, right? So at the classical level, there's no difference. We just always see Boltzmann. But when we go down to the quantum level, we see either Bose-Einstein or Fermi-Dirac. So how do we know when we're dealing with the simple classical world or the more complicated quantum world? Well, there's a condition that tells us. And again, if you were sitting in front of me, I would kind of ask you and try and drag it out of you. Maybe pause this and think about it for a minute. What is that condition when we know we can use the classical distribution and not one of the 2 quantum distributions? So for a hint, go back and look at lecture before last, or last lecture, when I was talking about, I guess it was 2 lectures ago, because when I was introducing the idea of indistinguishable particles. So pause, think, and now we're back. So that condition is when the de Broglie wavelength is much less than the average, I'll just rewrite the whole thing. When the de Broglie wavelength is much less than the average separation or average distance between particles, right? So this caret, that means average or expectation value. So when that average distance between particles is much, much greater than the de Broglie wavelength, it means that the particles don't really get jumbled up, right? Or at least jumble up so infrequently that we can assume that they're not jumbled. Okay, so that only happens when we have things happening on the scale of the de Broglie wavelength. So we know that the de Broglie wavelength is lambda Planck's constant over the momentum. And we know that there's an easy relationship of momentum and energy, or kinetic energy at least. I'll write kinetic energy as E sub k because we'll also use Boltzmann's constant, which is k. Right, so this is just our regular relationship between momentum and kinetic energy. But then we know the energy of some sort of gas from the equipartition theorem. You know the kinetic energy is going to be 3kT over 2 for a 3D gas. Oops, square root h. And then, of course, we simplify to 3 mkt square root under h. Okay, so most of what I'm doing is also in the book. So maybe if you find this confusing, go and read that, or read that first and then read, or listen to this. Okay. So now to ensure this condition, we know what's going on with the de Broglie wavelength for a 3D gas. Now we need to think about what would be average separation, and that's pretty straightforward. Average separation is going to be the volume of the gas divided by the number of particles to the 1/3. Right? You imagine that if I just had a line, a 1D system, right? When the analog of volume for a 1D system is just the length. So I have a line of some length, and I scatter some number of particles on there randomly. Right? It's just the average distance between them is just how long the line is divided by how many particles I've scattered on there. But if I make this 2 or 3D, right, there's more ways for these particles to be distant from each other. Okay, so I get a factor of 1/3 here in the exponent. Just sort of like our Pythagorean theorem in 3 dimensions. Okay, so now we know what D is, and now we know what the de Broglie wavelength is. And we just combine those two equations, and we get our condition so this we could call this condition for classicality for a 3D gas. Gas has 1 S. So N over V times 3m kt 3/2 under h cubed, much less than 1. Right? As long as this holds true, we have a classical gas. Okay, so let's do a couple examples. I'm just going to take an example straight from the book. This is example 8-6, statistical distribution of helium in the atmosphere. So H4 particles have spin 0 and hence are bosons. Right? The individual protons and electrons have some half-integer spin, right? But if I have 2 half-integer things, right, 2 half-integer spins, they can be pointing in the same direction, and then they can be a full integer. They can be pointing in opposite directions, in which case they cancel out. So if I have an even number of particles, well, they always have to be in an integer spin state, so they always have to be bosons. So helium-4 atoms, even though they're composed of fermions, in total are bosons. Okay, so helium makes up 5.24 times 10 to the negative 6 of the molecules in the atmosphere. Can the Boltzmann distribution be used to predict the thermal properties of atmospheric helium at room temperature, right? Or I guess at 273 degrees Kelvin, which is a bit cold for room temperature. So Boltzmann at T equals 273K. And part B, can it be used for liquid helium at temperature equals 4.2K? So I paused a little bit because the book explains this in an extremely confusing way. So I'm going to explain it in what I hope is a better way. The book says n sub 8 atoms of air occupy 2.24 times 10 to the negative 2 meters squared at standard conditions. A better way to say that is that one particle of air occupies about 2.24 times 10 to the negative 2 meters cubed. Okay. So then the number of atoms per unit volume, so this is essentially volume per air molecule. So number of atoms in that volume is equal to 6.02 times 10 to the 23 times 5.24 times 10 to the negative 6. So Avogadro's number, I think, if my memory doesn't fail me, times the proportion of those particles that are helium-4. Okay, so total number of particles times proportion that are helium-4 divided by this volume per particle, which is 2.24 times 10 to the negative 2. Okay, so that means there are 1.41 times 10 to the 20 molecules of helium per meter cubed. Okay, so that gives us this guy here. So then the left side of this whole equation, because we know H, we know M, we know K, we know T, right? I guess they're expecting us to look up the mass of a helium atom. This is not given here, but I guess it's in the equation. So we multiply all those numbers together. 3 times 1.66 times 10 to the negative 27 times 4 times 1.38 times 10 to the negative 23 times 273 to the 3 halves